Okay, now back to what I was saying before. All right, here's what we're going to be talking about. We're going to be talking about dark energy, and in particular, some of the ways that we might be able to look for dark energy and some of the challenges that you face when you're confronting the existence of dark energy in the first place. And so this is going to be covering a whole bunch of kind of related topics that's all related to the research that I did when I was a postdoctoral scholar at the Fermi National Accelerator Laboratory. And so there's going to be a number of things that are all mixed together in this one. I didn't have, please forgive the crudity of this model, I didn't have time to build it to scale. So there's going to be some stuff in this presentation that's a little bit afield from what we're talking about, but it's going to be great anyways, I think, because who doesn't like talking about physics, especially physics of the dark sector. So, and I'm stealing this from a talk that I gave a while ago, so this isn't like completely going from scratch like I usually do. But anyway, this is what it is. So welcome aboard. This is what we're going to be doing today. All right, now the dark sector. We know from a variety of measurements about the existence of dark matter, dark energy, and gravity. Well, gravity is part of, I mean, this is what I call the dark sector because it makes it sound cool. And so you can give a talk that's like the dark sector. And so that's what we did. We have talked about Big Bang nucleosynthesis in the past, where because of the, let me see if I can make this a little bit bigger. Whoa, that's way bigger. And another thing that would help is if I were to reposition this. And even if I were to shrink it a little bit. Okay, back to this. Now it looks bigger and I can, oh, that's so amazing. Okay, here we go. Back to where I was. We talked about Big Bang nucleosynthesis. Big Bang nucleosynthesis is the way, which is the fabrication of the light elements. So these are elements like helium-3, lithium-7, deuterium. All of these things were created in the early universe in the first 10 or 15 minutes of time of the early universe, when everything was super hot, super dense, and there were lots of particles bouncing around, protons and neutrons smashing into each other, some of them sticking together in the window of time between when the temperature was low enough for them to stick and stay stuck and when the universe was young enough, or the collision time between successive bounces of the different particles was short enough that the neutrons were able to survive from one collision to the next. Because neutrons only have a 10-minute lifetime. And so if the collision times between different particles is longer than 10 minutes, then the neutrons are going to decay away, and then that's going to shut down the process of nucleosynthesis. So this is Big Bang nucleosynthesis. We can measure the relative abundances of hydrogen, helium, deuterium, lithium-7, helium-3, some boron. We can measure those relative abundances and constrain the total amount of matter that exists in the universe, and it turns out that it is 4%. What else did we talk about? So we know from the growth, this one is the Sloan Digital Sky Survey. The distribution of galaxies measured by the Sloan Digital Sky Survey. And this graph shows basically the growth of structure. If you go back in the distant past, you can see that some galaxies are forming and how those galaxies start to cluster and how their clustering properties change as you get closer and closer to us, which means as you get more and more recent in the future, because light takes a while to travel to us. And so the distant galaxies were actually observing the universe in the past. So you can actually get the fact that light doesn't travel instantaneously from one place to another means that you can actually see the history of the universe, because you're looking at distant galaxies when they were younger. And then as you get closer and closer and closer, you see the galaxies more recently in the history of the universe. So you can map out the growth of large-scale structure and constrain the amount of dark matter or total matter that there is in the universe through the growth of large-scale structure. You can measure, so this plot down here is a collage of the type 1a supernova that were measured by, in this case it was Sloan Digital Sky Survey, but there were a few other earlier surveys to measure type 1a supernova, which are stellar explosions that act as standard candles that allow you to measure the luminosity distance, which is basically how do things get dimmer as you get farther and farther away from them. And that was able to determine the presence or measure the presence of dark energy. And then we have the cosmic microwave background radiation, which is what we just saw in the astronomy picture of the day, which tells us the total amount of everything, the total amount of combined energy in the universe. So it turns out, from the cosmic microwave background radiation, we know that the universe is flat, meaning that the amount of energy in the universe is equal to what's called the critical density. So the energy density of the universe is equal to the critical density, which, if the universe was completely made out of matter, the critical density is the amount of matter in the universe that would allow the universe to expand, but it would expand with bound. So it would expand and it would go slower and slower and slower as it got bigger, because its own gravity is pulling it in, but it's still moving away, and so it eventually slows down. And in the infinity future, it would essentially come to a stop. That it never completely stops, right? You just keep adding a few digits to the size. That is a flat universe if the universe was made completely out of matter. But we know that the universe is not made completely out of matter, but that still gives us this critical density that is called flat. So here's flat. If the total energy density is less than the critical density, then you have what's called an open universe. So that's this thing right here that says open. And then if you have more energy density than the critical density, then you call it a closed universe, where if it was made completely out of matter, then the universe, the gravity would pull everything back together again, and then we would all die in a big crunch, and it would be amazing. Or the open universe, where the universe expands without bound into the future. Yes, we do have VODs, and I do have a YouTube channel where I put these things. Okay, so this is the cosmic microwave background radiation right here. That showed that the universe was flat. So you can see that the error ellipses in the cosmic microwave background radiation determination of the relative amount of dark energy and dark matter. So this is dark energy in the vertical axis relative to the critical density. And the total matter, that includes regular matter and dark matter, in the whatever this is called. So this is total matter in the universe as a fraction of this critical density, and this is the total, or I'm sorry, let me say this precisely. This is the total matter density relative to the critical density, and this is the total dark energy density relative to the critical density. The cosmic microwave background radiation is this ellipse that's right here, and it lies very near, not exactly on, but close enough that we can pretend that it's exactly on this line that goes from +1 here to +1 there. That is that line is where the sum of the dark energy density and the dark matter density, that is the line where the sum of the dark energy density and the matter density, total matter, regular matter and dark matter, it's basically all dark matter. It's only 5% regular matter and 25% dark matter. But they live, this line is where they sum to 1. So you have like a half and a half right there, which sums to 1. You have 1 and 0, and you have 0 and 1. So that is the line where you are on the critical density, or the universe is flat, as we like to call it, because it makes us, because then we can say that in our talks and sound simultaneously smart and as though we're speaking to a general audience. Okay, so anyways, the cosmic microwave background tells us that the universe is flat, so that lies on this line. That's why the green error ellipse is roughly parallel to that line. Okay, next we have the growth of large-scale structures. So this is the growth of galaxies. The growth of galaxy clusters tells us about the total matter in the universe. It tells us, if there's a lot of matter in the universe, then you get certain properties in the growth of clusters. They grow quickly, and you get really big ones, and they happen really quickly. If you have very little amount of matter, then you don't get very many clusters. It takes a while for things to coalesce. And so by looking at the growth of large-scale structure, the growth of galaxy clusters, you can constrain the total matter in the universe. And that is why this error ellipse here, this clusters error ellipse, is vertical. That basically says it has very little constraint on the dark energy density. You can have almost any dark energy density that you wanted, because in the past, matter was more important than dark energy, and so you get the growth of clusters whether there's dark energy or not. It's basically independent of dark energy density. Again, it's not exactly independent, so there is a slight tilt to it, but we're going to ignore that tilt. We're going to pretend that it's vertical. And so that tells us that the growth of clusters tells us the total matter density in the universe. And that is why it is this vertical stripe. And so you can see that, lo and behold, when you have one line of the cosmic microwave background radiation, so that tells us the universe composition, it lies along this line, and the growth of large-scale structure, which is this vertical ellipse, long and skinny ellipse, that they both intersect. Lo and behold, when you have two lines, they cross each other at a single point. Well, that's great. So that tells us that the universe is likely, the composition of the universe, meaning the amount of dark energy and the amount of total matter, is probably going to lie in that intersection. But it'd be nice to get a third measurement of this property. And lo and behold, we do. We have the third measurement of that property, or of the composition of the universe. And that is these distant supernova. So the distant supernova, what does that tell us? What this says is, so this is the supernova ellipse. And a thing to look about this ellipse is if you tilt your head to the side, you'll notice that the ellipse is roughly perpendicular to the cosmic microwave background radiation. It's roughly perpendicular to this flat universe thing. So what does that mean? So what the supernova tells us that the universe is accelerating in its expansion. So we get an acceleration rate in the expansion. What this means is if you add more matter, you add more matter to the universe, if you still want the universe to accelerate, then you need to add more dark energy. So the more matter you add, the more dark energy you have to add. Or if you have less matter in the universe, then the less dark energy you have to have. So if, say, you have half the matter in the universe and you want to have a certain expansion rate, then you can reduce the amount of dark energy by that same fraction. And that's why the supernova measurements, it gives you an expansion rate. And so if you, with a given expansion rate, as long as you increase the matter density at the same rate that you increase the energy density, then you get the same expansion rate. And this is the universal symbol for expansion rate. And so that's why this air ellipse is in this direction. So when you add, if you add a little bit of dark matter, so that's moving in the horizontal direction, add a little bit of dark matter, you have to add a little bit of dark energy. And so you get this ellipse. And lo and behold, all of these combined measurements of the properties of the universe give us a unique composition in terms of the relative amounts of dark energy, dark matter that we get. And so yay for us, they all agree. It would be terrible or there would be a lot of explaining to do if this supernova ellipse were somehow down here, so that you had basically a triangle with a hole in the middle, because that basically says you have three simultaneous estimates for what the universe should look like, and that they all disagree with each other. Here we get, they all intersect at one single point, and that's, you know, we already know that if you have two lines, they're going to intersect at a single point, but if you have three lines that are independent measurements of the composition of the universe, then they, the fact that they all intersect at the same point means that we live in a universe, a single universe, and not a bunch of weird stuff, that we actually have some good idea about what we're talking about. Okay, now I mentioned this for a reason. I don't remember exactly what that reason was. So we talked about dark matter WIMPs. That's one of the candidates for dark matter. So I'm going to skip some of this stuff. And no, I won't skip it. I'll keep going. So non-relativistic particle with weak scale cross-section. Weak scale cross-section meaning like the interaction similar to weak nuclear physics. The strength of the coupling of the particles, the protons to the W and Z particle that allow for the nuclear decays. That's weak scale cross-section. So that's the kind of stuff that you measure in the Large Hadron Collider, and at Fermilab they're specifically designed to probe weak scale physics, to have interactions with couplings similar to those at the weak scale. Okay, so it turns out there was a thing that's often quoted. Some people don't like it, some people don't care. I'm one of the people that don't really care. The discussion of the WIMP miracle. So the WIMP miracle is that it turns out if you have a particle with a weak scale cross section, meaning that its interaction strength is on the order of this interaction strength of the W and Z particle to protons and neutrons, then you automatically get about this much dark energy, about the amount of dark energy that we observe. And so that's the reason that people are looking for weakly interacting massive particles, or WIMPs, is because if you have weak scale interactions and the particles have some mass, then you get the right relic abundance of dark matter. So there's infinity people looking for WIMP dark matter. So I was like, I'm going to tell a joke in my presentation because you always want to have humor. Who isn't looking for WIMP dark matter? Because everyone and their dog was looking for WIMP dark matter. And so no one wanted to do that. I didn't want to do that because why join a crowded field? And so I talked about Axions, which is the other dark matter, which is, I don't know, does anyone remember the television show where it was pork, the other white meat, from Murphy Brown? Anyway, so pork, the other white meat, this is Axions, the other dark matter. And then I talked about, and this is something that I've already talked about when I talked about, so there's a number of videos about me talking about Axions and dark matter. And I talked about the strong CP problem and how you need to clean it up because the strong force doesn't have CP violation in it. And that would give an electric dipole moment to the neutron, and because you measure this, you get a number that's close to 0, when in fact this number should be close to 1, and that's the strong CP problem. And so you invent a particle, you conjure up a particle to solve this problem that cleans up the strong CP problem, and you name it after a dishwasher detergent, called Axion, and this is all the stuff about axions. There's a whole lecture already about that. And then I talk about the early universe. Now, some of the things about axions that I didn't go into, that I guess I'll go into now. So the axions are a dark matter candidate that would form in the early universe. So talking about the early universe, when you start with really hot stuff and you spread things out and you cool them off, you go through a variety of phase transitions. So here's a plasma. This is at super high temperatures, you get a plasma where you strip off the electrons from the protons, and so you have ions and charged particles going through there, and so plasmas are opaque. Notice that the plasma is opaque, right? It looks like it's glowing blue, but that's actually opaque. If the air in here were more dense, then these would look like bolts of lightning. I mean, they look like bolts of lightning now, but that's partly because it's evacuated. The reason you can kind of see through them is because it's has a low optical depth. But if you were to have like a lightning bolt and the optical depth in the regular atmosphere goes up, then it would look even more opaque than this. Anyways, plasma. So that's super high temperature plasma. As the temperature goes down, then you get a gas, and as it continues to go down, you get water or a liquid, depending upon where you live in pressure space. And if you continue to go down, then you get a solid. So that is phase transitions that you get when you change the temperature or the density conditions in the universe. So if we look now at the cosmic microwave background radiation is very cold. So that's what we observe today. And when it happened in the early universe, this was like the last phase transition, because the electromagnetic field is the binding energy of electrons to protons in the atoms. So like the ground state energy of hydrogen is the lowest energy of the forces when you form something. So when you bind a neutron and a proton together, that is with 1,000,000 times the energy of an electron being bound to a proton. So if you take like the binding energy of helium, the helium nucleus is 1,000,000 times as energetic as the binding energy of electrons to the nucleus of an atom. And so that means that the nuclear physics is going to happen at temperatures that are 1,000,000 times higher than the temperature where the electrons are going to be bound to the atoms. And so this cosmic microwave background radiation is showing that this last transition happens when in the early universe it cooled to that point, and this is the coldest transition that you go through. So if you raise so you go back further in time in the universe, you get higher and higher energies, or higher and higher temperatures, which means that you're going to have higher like physics that happens at higher energies. And so Big Bang nucleosynthesis that I've also talked about is 1,000,000 times the temperature of the cosmic microwave background radiation. It happens, this process takes place at 1,000,000 times the temperature. Okay, and then if you go back even earlier, you get the quark gluon plasma. Now this is something that I'm going to be talking about one of these days coming up in the future, is this experiment right here, the relativistic heavy ion collider, and also the LHC does it as well. This is actually kind of interesting because these, the LHC in one of its operating modes, which is the heavy ion collision operating modes, and the relativistic heavy ion collider, which is at Brookhaven National Laboratory, that is, these are actually examining the really, really early universe before you were able to even form protons and neutrons. This is looking at the behavior of quarks and gluons, the constituents of protons and neutrons, as they, when the universe was extremely dense and very high temperature, there were no protons. There was just quarks and gluons flying around. And that's what these things are able to measure. So they're measuring the behavior of quarks and gluons in these high energy and high temperature environments. So that will be a discussion for another day, because we can't talk about everything all day, every day. All right, and then you go even earlier than that, and then you probably have some Planck scale weirdness, like at super duper high temperatures and super duper high densities. Then you have to worry about what happens to gravity. You have to have some theory of quantum gravity. And right now we don't have, we have theories of quantum gravity, but nothing that's been explored experimentally in any reasonable thing. Now, one of the things that's important about axions is that you need to, when you produce axions, it happens between, because of the, I'm sorry, let me try that one more time. If axions are the dark matter and they were produced in the early universe, they were produced through what's called spontaneous symmetry breaking. And so I've got this amazing analogy that I'm going to share with everybody because I did it in Mathematica, and that makes me feel proud of myself to know that I can do these kinds of graphs in Mathematica. So in high energy field, it sloshes around in its potential. So you have some field that exists. So this could be like an electron or electromagnetic field. It could be some other kind of field. In this case, it's going to be the axion field. And it lives in some potential, which means that it gains some energy if it moves in some direction. So you have a field, it has some value someplace, and if that value changes, then it gains potential energy. So this is the surface that maps out the potential energy that you gain if you add fluctuations to that field. Okay, so here's what it looks like. Here's the isometric views of this axion field. Now, one thing that's important to note is that if you want to probe the structure of this electromagnetic, if you want to probe the structure of this potential, that we have here, you need to understand what it is that you're measuring. And so I have the analogy. I mean, people say like this is all fine and good, but what does it have to do with the design of women's shoes? And I'll tell you. Okay, so this is a cobblestone road, and this is the kind of road that you would see, like, say, in Paris. And I was with my wife going around in Paris, and her ankles were getting really tired at the end of the day and couldn't figure out exactly what was going on. But she said that, and so she just wore tennis shoes on the next day. But turns out I started looking at what were the local women wearing, on what kind of shoes were they wearing as they were walking around on the roads that look like this, because they didn't seem to have the same kind of problems. You know, like certainly they're getting tired. Why would they even wear these shoes if they're out here all day? It's one thing for tourists. It's another thing for people who are local. And it turns out that the shoes were different between what my wife was wearing and what the local French women were wearing. So my wife was wearing shoes that looked like this. So it's kind of a high heel and about a 1-inch pad on the bottom. And this is what the roads look like. Okay. The French women, on the other hand, were wearing one of two different kinds of shoes. Even though they were also heeled shoes, there were two different varieties. The French women were wearing either shoes that looked like this, or they were wearing shoes that looked like this, which I don't really care for either. Okay, so they either had shoes with really small heels or shoes with really big heels. Okay, now, why were they able to do this without getting tired and my wife was getting tired? Well, the answer to that question comes down to the size of the heel. And in particular, the size of the heel relative to the gap in between all the cobblestones. So if your heel was the same size as the gap in the cobblestones, then you happen to be very sensitive to the size of that gap, because every time you step, your heel is going to be, well, a large fraction of the time when you step down, your heel will be on the border between these cobblestones, and your heel will flop back and forth because it's not a stable platform. Where on the other hand, if you have a very small heel like this one, then when you step on a gap, the heel actually goes between the cobblestones. And if you have a really big heel, then the heel will span the entire gap between the cobblestones. So the worst, in terms of stability, the worst size heel to wear is the size of the heel that is similar in size to the gap between the cobblestones, because that's where you're going to hit an edge. It's too big to fit in the gap by itself, but it doesn't span the whole gap very easily. And so when you hit the edge, it means that sometimes the heel is going to get jarred to the left or to the right. So that's important to know. This is the same thing when you go hiking up in the mountains. When you go hiking in the mountains, the size of you want to be careful the kinds of rocks that you step on. If you step on gravel, like really small rocks, that's fine because your whole foot will span many pieces of gravel. If you want to step on gigantic big rocks, that's fine as well because your whole foot will land on a single rock and you'll be stable. The worst size rock to stand on or to put your foot on when you're hiking is a rock that is about the same size as your foot, because then you get the maximum distortion in your ankle when you step on a rock like that. So the same idea is going on here. If you want to probe the properties of a given feature in a surface, you want to probe it with a particle that has basically the same wavelength or the same energy as the thing that you're probing. This is what I talked about before. This is the field the axion field is sloshing around in, the potential that the axion field is sloshing around in. Okay, and but if you zoom down, if you cool things off, that means that you're probing things at smaller and smaller energies. So as the energy of the universe cools down, you're probing features at smaller and smaller energies. And so this is the same field. It's just now I'm zoomed in at smaller scales. It looks like this. Okay, at lower temperature, it reveals a new feature. So now, instead of something just rolling around in this bowl, now you have this feature in the middle because you have a low energy particle. So small hills are going to make a difference. This hill is actually the same size as this one. I just cut it at a lower vertical point. So now it's going to be able to see, oh, there's actually two directions here. I can either roll around on this hill, or I can roll over the hill, or I can roll around the hill, like around the moat. So I can slosh in the radial direction, or I can slosh in the azimuthal direction. And it's the same structure. It's just now we're looking at it with lower energy. So as the universe cools, if there's features in the energy landscape that are smaller, as the universe cools, it will discover them, and the symmetry will break. Okay, the symmetry will break, and that is called spontaneous symmetry breaking. And the analogy here is that if you have a spherical cow and you have two identical haystacks, that the cow will not starve to death. Eventually the cow will choose one of the haystacks and start eating. And so spontaneous symmetry breaking is basically, in this case, what's going on with spontaneous symmetry breaking is you have some value of this field, some value of the axion field, and it's going to all of a sudden see at one point this peak. And now it's going to have to choose what direction. So it's going to be located, in general, it's going to be sloshing around. So at high energies, it's just moving around here. Its average position is right in the middle. But as the energy of the universe drops, then that axion field is going to have to choose which direction it's going to roll down the hill. It's eventually got to roll down the hill because it doesn't have enough energy to stay at the top of the hill. So it's going to have to roll down, and it's going to have to roll down in some direction. And if there's no reason why it should prefer one direction over another, then it's just going to choose a direction at random. And that's the spontaneous symmetry breaking. There is a symmetry, but eventually that field is going to have to choose some direction that it's going to misalign, or that it's going to deviate from the center. And that will be the choice of the universe. So that's spontaneous symmetry breaking. Okay, then something else happens. There's yet another feature in this that might be hard to pick out, but you'll notice that the left-hand side of this little bowl here, if you squint and look really close, you'll notice the left-hand side of this bowl is a little bit higher than the right-hand side of the bowl. So you have this axion field that used to be sloshing around, and then it saw this tip and it had to roll down the hill in some direction. But turns out there's another feature at really small scales, and that is this tilt right here. And so now you have this axion field located at some point in azimuth, but now it's able to, the energy of the universe is low enough that it's able to see that this is actually not completely flat. It's actually tilted in some direction. And that's going to cause the axion field, wherever it started, to start sloshing around like this, start oscillating like that. And that is how you produce the axions. It's that motion there that produces the axion particles. That could be the dark matter if they are the dark matter. So this is called the Pechequinn symmetry. And there are a number of things about the early universe that the question becomes whether this tilt, I'm trying to remember exactly how this works. I probably shouldn't have done this because I would need to have, I should have looked it up to make sure that I'm pretty confident that this is the right story. So I apologize for any delays in telling this story. The question becomes, this tilt here happens at the QCD phase transition. So there's a point in the early universe where quantum chromodynamics becomes important, the QCD phase transition, and that's what causes the tilt. So temperature falls, reveals a new feature. The QCD phase transition induces a tilt to this potential, and the axion field starts oscillating around there. So that is the, this comes from physics that's to some extent unrelated to the axion. Right? This is, well, it's clearly not completely unrelated to it because it changes the axion potential, but it's different physics, right? This is physics of the strong nuclear force, causes a tilt there. And then the question becomes, because you have a few options, it's not obvious, in this case, as you cool it down, this, the axion field broke before the QCD phase transition, but you could have it happen in a different order, where the QCD phase transition happens first, and then the axion field shows up, and then the peak in the center shows up. So I could imagine constructing the same potential, except having the slant be a larger energy scale than the bump in the middle. Okay, and that will give two different universes. It turns out that the axion density is related to how big the oscillation is. And so each different patch of the universe, because the universe isn't, when you go through this phase transition, different parts of the universe aren't going to be talking to each other. It takes time for light to travel from one place to another. So you could have two different regions of the universe where the spontaneous choice of the axion field, or the Pechequinn field, I think it's the axion field, chooses one direction or another. So maybe in this part of the universe, it chooses up as the direction where it wants to go down the hill. And then in this other part of the universe, it's going to choose to the left. And so in one part of the universe, the axion is up here, resting up here, and the other part of the universe, the axion is resting over here. And then you go through this phase transition, which means that one part of the universe is going to have one amplitude of oscillation, and a different part of the universe is going to have a different amplitude of oscillation. And some parts of the universe might have a really tiny oscillation, and some parts of the universe might have a gigantic oscillation, as big as you can get, basically, because the QCD phase transition tilts everything all at once in the same direction, but different patches of the universe that had no reason to have their physics develop uniformly with anybody else, right? It's a spontaneous symmetry breaking, and one part of the universe doesn't necessarily know what the other part of the universe chose, right? There's no way to communicate between those two parts of the universe because it would require that you travel faster than the speed of light. And since things don't travel faster than the speed of light, you have different things. So the universe is basically made up of a bunch of patches of different regions, disconnected regions, at least in the past, disconnected regions, where they each chose some unique orientation or unique angle that the axion field went down this Mexican hat potential, or the wine bottle potential or Mexican hat potential, whichever, however you want to call it. They mean the same thing. Okay. So then another thing that happens in the early universe. Oh, okay. I just remembered what I was supposed to say earlier. So I apologize for this. I'm going back and I'm going to correct the record. There's another phase transition that physicists believe happened in the early universe. So this happened in the order that I told you. So I'm going back and correcting the record. This happened in the order I told you. You first choose the direction that you go, and then you go through the QCD phase transition. That's always going to happen in the same order. What I missed was there's another transition that happens in the early universe that is there's another transition that happened in the early universe that many physicists believed took place, and that is inflation. So we don't have evidence for inflation yet, but there's strong reason to believe that the universe went through a period of inflation. And the question is, when did this physics happen relative to inflation? That's what I should have said earlier, but I'm remembering this as I go, so please forgive me for that. Highlighted message. So string theory would not matter here if part A doesn't know part B's physics. Yeah, so this is way, way after any string theory would happen. So string theory, that's super, super high energy, and it's much earlier than this. This is basically low energy physics, because the QCD effects, the QCD phase transition, that we measure in accelerators. So that's something that we can reach on the Earth. Okay, so back to where I was before. So we have two different important events that are happening in the early universe. It's the production of the axion field or the inflation. Which one happens first? We don't know, because it depends upon what the energy of inflation, like what energy or what temperature inflation takes place. So it turns out that so breaking the speed of light with pulses inside of plasma, is this real, new, or useful? So the thing about physicists breaking the speed of light, it has to do, there's a Sabine Hofstadter, I think is Hassenfelder. She has a discussion about what's actually going on with that, where you have you're looking at the spreading out of the wave function, and it turns out that you don't actually get you don't break the speed of light. There's a way of interpreting it in quantum mechanics that doesn't break the speed of light, or that doesn't where that is the wrong, where breaking the speed of light is the wrong interpretation, and I agree with her in that. Okay, so the question is, when did inflation happen? Okay, so here's the other phase transition. You have inflation, this is, inflation is here on the right, and you have the Pechequinn symmetry that produces the axions on the left. And does inflation happen at higher energy? So does the inflationary part of the universe happen before this phase transition, or does the inflationary period happen after the Pechequinn symmetry breaking? So if axions are the dark matter, which everyone believes, of course, that they are, if the axions are the dark matter, then it really matters whether the production of the axion field happened before or after inflation. And here's why. Inflation took a universe that is this big and very quickly turned it into a universe that is this big. Okay, great. Well, what does that mean? Well, what that means is if inflation happened before the axions, so if we take this one right here, so inflation happens first, so the universe, remember that the universe is cooling down. So the higher energy stuff happens first, the lower energy stuff happens later. So as the universe is cooling down, if inflation happened first, that's this, and then you produce the axions, then here's what happens. Here's a patch of the universe. That patch of the universe expands, and then you get axions. And so different parts of the universe actually have different axion properties. Okay, and eventually, as the universe starts to mix around, these axions have mass, and so they move slower than the speed of light. So they start mixing around, and you get an average of all of these mixing angles in the universe that we see today. On the other hand, if inflation, if we look at this and the axion was produced first, and then inflation happened, then this is what you get. So here's the patch of the universe, and then you get axions produced, and then the universe expands. And so you only get one type of axion, like you get a single universe where all the axions have exactly the same properties. And these are two different outcomes, right? This phase transition is not, it's not transitive. You can't do it in any arbitrary order. If inflation happened first, then you start with a patchy universe, you inflate, and then you produce axions. And what we observe today is the mixture of all these different axion properties. Or inflation happened second, and you start with a patch of the universe, you produce the axion field, and then you inflate, and you get one misalignment angle. So that's actually important, and is related to the properties of the dark matter axion that you might expect to have. Okay, it turns out that back in the day, not long ago, there was this bicep measurement. So the bicep measurement here showed, well, at least initially, it was interpreted as the discovery of inflation. And so what the bicep measurement was, is they looked at the polarization of the cosmic microwave background radiation. So you have the cosmic microwave background radiation out there, and the light coming from different directions is going to be polarized. You know, it's maybe in general it's random polarization, but in a particular direction you might have some preferred polarization, and this would be leftover signatures of the of inflation. So if inflation happens, it's going to produce these kinds of swirls in the polarization signal of the cosmic microwave background radiation. So instead of having random polarizations at every point in space, you're going to have these kinds of swirls. They're called B modes. So B modes are things that swirl around, where E modes, if you call them E modes, those are things that point directly outwards. So let me see if I can, let me draw a picture of that. So B modes are things that look like this. Here's a point in space. The B modes are ones that look like that, where the polarizations basically spiral around or circulate around a particular point in space. Where the E modes, and this is related to magnetic fields and electric fields, that's why they call them that, even though in this particular case, it's analogous, where it doesn't really have anything to do with electric or magnetic fields, other than it's the polarization of light. They call this B mode because magnetic fields, if you have a current flowing through a wire, you get a magnetic field that spirals around, so they're called B modes. And if you have an electric charge, then E modes are things that point out like this. So E modes look like this, they point away from a given point in space, and B modes look like this, they basically curl around a point in space. And so that's why they call them B modes and E modes. Well, here is the bicep B mode signal. And the presence of a B mode signal is an indication of inflation. That is a signature of inflation in the early universe. So this was measured, And this type of thing actually points to this scenario. These B mode oscillations pointed to a scenario where you start with the early universe like this, then you inflate, and then the axion is produced. So that means that inflation happened here. Inflation happened at higher energies, and then you produce the axion dark matter. Okay, this was important for my group because we were looking for axion dark matter, and this would tell us whether we should look for axions that come from this type of variety or axions that come from this type of variety. Okay, now it turns out, so this totally changed the trajectory of the research group I was working with. I was thinking about designing an experiment to look for axions of one type, and then these results came out and excluded that region. Basically, there are two different types of axions here. There's really low mass axions, and there's kind of high mass axions. So this area is allowed, and this area is allowed. This is the mass of the axion on this vertical, or on the horizontal axis, mass of the axion, and its coupling. And so if you have really low mass axions, the only way you can have low mass axions is if the axions are produced first, and then you go through inflation. That is where you can have low mass axions. The high mass axions, they are produced this way, where inflation happens first and then the QCD phase transition. Well, it turns out that the B mode gave us an inflation scale, and that inflation scale pointed to this type of axion. And so the experiment that I was designing that was specifically looking for this type of axion was eliminated as a realistic possibility. And then, of course, after we changed trajectories and we stopped working on developing this experiment, it turned out that this signal is dust, comes from dust in the galaxy. You have different patches of dust in the galaxy. Those dust grains will happen to rotate because dust grains tend to be kind of arbitrary shapes, like unusual shapes. They're not spherical. There's some arbitrary shape, which means that they can spin. And when you have spinning dust, when the cosmic microwave background photons hit it and interact with that dust, they will come off with a particular polarization. And so this signal turns out to be fake. It's not fake, it's a real signal, but it's a real signal of dust in the galaxy, which means that we have not yet discovered inflation, which means that this was not actually excluded, which means that we could have built the experiment that I was originally working on, but we didn't. So anyways, that opportunity passed away, or passed us by. So a couple questions have come up. Let's see. The axion field is what you're illustrating with the small circle. Yes, that's the misalignment angle. The small circles here are the misalignment angle that the axion field has when it goes through. It's chosen a direction, and then you get a tilt. And the question is, where is the direction that it chose relative to that tilt? So if it started here, the tilt is along the, in this case, the horizontal axis. And so if it started here, then the misalignment angle would be, well, that angle, 135 degrees or whatever. Or if it started here, then the misalignment, if it started at this point, then the misalignment angle would be 45 degrees. So this is basically the misalignment angle that you get for each of these different patches of the universe. Okay. Inflation is real, look at my wallet, exactly. All right, let's see. What would the universe look like if inflation never happened? That's a great question. If inflation didn't happen, then there would be some mysteries that need explaining. So I guess I'll go into some physics of like why we think that inflation happens. The reason we think that inflation happened is as follows. We have a few problems. And the problems all stem from the fact that we have different parts of the universe that, well, okay, I can pull up this picture actually since it's on here. Okay, so this is the cosmic microwave background radiation. This side of the universe, this side of the cosmic microwave background radiation, the light from this part of the universe just reached us now. So it's been traveling for 13.7 billion years, minus 400,000, to arrive at us. That's in one direction in the sky. This patch of the universe is in the opposite direction of the sky, and it is coming towards us, and the light from this part of the universe has just reached us now. So the light from here and the light from here are just arriving at the halfway point between the two sides at us, and the temperatures are identical to within 10 parts per million. So that's a big, like, that's a big issue. Why is this side of the universe that has never spoken to or exchanged information with this side of the universe at the same temperature to a part in 10 to the 5, a part in 100,000? So that's a thing called the horizon problem. So let me come back to this drawing pad so that I can use my amazing handwriting skills to say we have, again, did it again. Anyway, so it's the horizon problem. That's a Z, horizon problem. There we go. The horizon problem. The horizon problem is that you have one side of the universe that's at the same temperature as the other side of the universe, even though they're beyond each other's horizon. So, for example, what that basically means is here is one side of the universe, and it has a horizon, which is basically how far could someone who lives here see in the universe? And the answer to that question is they would be able to see us. So here's us standing right here in the middle. The person on this side of the universe would be able to see to us. And now on this side of the universe, how far could that person see? And the answer to that question is it could also see just to us. So this is the horizon. Okay, pretend that these things are centered on that point. This is the horizon. We are at the horizon of someone over here, and we are also at the horizon of someone over here, which means that the person here will make it a 4-legged person, and the person here will make it a 6-legged person. These two people don't know about each other. They don't know about each other because there's no way for light from this side of the universe to make it all the way to that side of the universe. It's beyond the horizon. They can't see that far. That is the horizon problem. And so the question is, we're sitting here looking at these two things, and this one has a background temperature of 2.7 Kelvin, and this one has a background temperature of 2.7 Kelvin. Why do these agree with each other? There's no reason for them to agree with each other. If you take two different groups of people that have never communicated on opposite sides of the earth, why do they both speak English? Right? Or it'd be like discovering them both speaking English. It's like when alien civilizations come and visit the earth, they all happen to speak English. Okay, so that's some creative liberty on the part of the writers, but that's essentially what's going on here. That these two distinct parts of the universe that have never communicated with each other are at the same temperature. That's the horizon problem. Another issue that we face is related to the cosmic microwave background radiation again, if we come back up here to the top, and that is, why is the universe flat? The universe could have chosen any number on here, except for being negative, I guess. The universe could have chosen any number on this whole plane, on the whole half the plane. That's infinity different numbers for the total amount of matter and energy. So the total amount, it could have had, 2 and 1. Could be up here. The universe could have been over here. Could have been down here. Why did it choose this? Why did it choose to live on this line? That's called the flatness problem. Why is the universe flat? It could have any curvature that it wanted. It could be saddle shaped. It could be spherical shaped, and it chose to be flat, which is unusual because there's only one part in infinity where you get that value. So why is the universe flat? So that's problem number 2, is the flatness problem. Flatness problem. Okay, and then the third problem is, why is the universe, why do we get the growth of structure that we see? Okay, why is the universe have the galaxies spread out the way that we expect them to be? Because if the seeds of galaxies turned out to be from quantum fluctuation in the early universe, then we would actually expect the universe to be more clumpy. We would expect more dense concentrations of things, and they'd be closer together. Okay, so that is called the smoothness problem. And it actually, this one has a bunch of different names, but I call it the smoothness problem because that's how I learned it when I was an undergraduate. So that's the smoothness problem. M-O-O-T-H-ness problem. That says problem. Okay, so we have the horizon problem. Why are different sides of the universe that have never spoken to each other at the same temperature? We have the flatness problem. Why is the universe flat when it should be any value, or could have been able to pick any number that it wanted and it chose 1? And then why is the universe as smooth as we observe it? Those are the things. And so inflation solves all of these things at once. The inflation says, okay, we could have started with a universe that looked like this. It was highly curved. It has highly curved, so it's not flat. And it's really bumpy. So there's really bumpy on it. So there's lots of clusters of matter in different places, but it's small. Small. And because it's small, this side of the universe can exchange information with this side of the universe. So it stays small for a while, and information gets shared all around this curved universe. Okay, that means everything goes to the same temperature. Once everyone can communicate with each other, they all agree on what temperature they should be. Because if there's a overdense or if there's a high energy region, it will share its energy with the neighboring regions and it will all come into equilibrium. Then you go through this inflation period, and now all of a sudden the universe grows like mad. And so now the universe looks like this. It's inflated from a small sphere into a gigantic sphere, or it could have been a small saddle that expanded into a gigantic saddle. But now here's us on this thing, and we look off in these different directions and we say, flat. Okay? It's that the curvature of the universe has expanded so much, or the radius of curvature of the universe has expanded so much that it looks flat to us. We aren't capable of detecting the fact that there's still some small curvature to it. That maybe if we were able to measure the curvature of the universe to, right now we're at about 1%. So if we were to maybe crank this up to 100,000%, or is that a million? 1,000,000%. That's actually the wrong direction, isn't it? Okay, 1/1,000,000th of a percent. If we were to go to 0.000001% in our precision, maybe we would see curvature at that point. But for now, it's consistent with flat. So we take this universe, we expand it very rapidly, and so it does, one, it started small, so everything gets to the same temperature. Two, it expands very rapidly, and so the universe becomes flat. And three, it takes all these big fluctuations and spreads them out and makes the growth of structure more smooth, makes the galaxy clusters more smooth. They're less prominent, they're more spread apart. And that is this is the reason why we think that inflation exists, is that it solves all these problems at once. If you have a theory that solves one problem, yay, I mean, every theorist and their dog knows how to do that. If you have a theory that solves two problems, like the Axion, solving both the strong CP violation and the dark matter, then that's a really interesting theory. If you have a single theory that solves three problems, then it's a really, really interesting theory. So it's like really, really to the n-1 interesting. Okay, where n is the number of problems that you solve. So if you solve one problem, then it's just interesting. If you solve two problems, then it's really interesting. And if you solve three problems, then it's really, really interesting. So you can imagine having a theory that solves four problems at once. Hey, Demon Machine, thank you for that raid. I appreciate that very much. Yeah, you want to make sure that you use your pets when you're doing math. Now, there are problems with inflation. There's a book. It is a very thick book, very dense book, called The Road to Reality by Penrose. Complete Guide of the Universe. Where's the author? Roger Penrose, right there. Okay, so this book, Road to Reality, and he actually complains that inflation is given a little bit too much credence relative to things. He's even got a picture in here that's like, why would the universe start at such a low entropy state? Do I have it marked? I don't have it marked. Anyways, so it's not that that inflation has its problems, but it does solve these mysteries that we have. And that's why we think that inflation happened. That the universe started very small and expanded rapidly, took care of the horizon problem, took care of the smoothness problem, took care of the flatness problem. However, right now there's no evidence for inflation aside from the fact that it's a theory that explains a bunch of stuff, that resolves a bunch of mysteries. Okay, so that is inflation and why we think that inflation should happen. All right, and we talked about this, and we talked about this, and we talked about Pechequinn symmetry, and we talked about spontaneous symmetry breaking. We talked about why we would look in axions at different masses. We talked about why the fact that inflation happened, and we know the energy scale that inflation happened. So there's like, these are the measurements, or this is the result that came from that. That you have the axion mass and stuff like that. And here's the bicep result. So they're basically two different areas where axions could live. They could either live on this side of this particular plot or this side of this particular plot. And we have the bicep results over here that says, oh, it has to live on this side and it can't live on this side, which means that you have to build this type of experiment and not this type of experiment. And that means that we did not do the experiment that I was looking for. Instead, we're doing this one. These are the misalignment angles, I guess. So I was doing an experiment that was going to be looking up in this area with small misalignment angles that you can only have in this thing, because if you have a small misalignment angle, which is what you get up in this part of this parameter space. So this is the misalignment angle here, at least these theta i's, and then this is the inflation, H inflation. So that's the inflation energy, basically. The energy scale when inflation took place. So I was going to be looking for stuff up here, which means small misalignment angles. And the only way that that can work is if you have the whole universe at a small misalignment angle. If, on the other hand, you have a universe with an average of all these misalignment angles, then the misalignment angle is going to be of order pi. And so that's what's down here. So the misalignment angle down here, where you're averaging over a whole bunch of stuff, means that the typical angle is going to be something on the scale of pi. And you see right here, the misalignment angle 3.14. That is close to pi, and it's right here in this area. So that eliminated, these bicep results eliminated low misalignment angle axions and favored this other one. Okay, what else is on this? I don't think I'm going to make it all the way through this thing, but we'll keep going. We're going to keep going, see how it goes. All right, some numerology about why we should care about some of this stuff. All right, I've mentioned before that when the dark energy density is the milli-eV scale. So when you set E equals mc squared, and then you say, what's the Planck size, or like, what's the size of the of a box? Okay, let me try this one more time. We're gonna go like this. It turns out if you set C equal to 1, then you get E equals mc squared, which means that E equals m. So energy and mass are the same. You also set, physicists will set H bar equal to 1, or H equal to 1, one of those two, depending on who gets to decide whether 2 pi is equal to 1 or not. So the units that physicists use to measure, the high energy physicists use to measure things, they'll set C equal to 1, so then they don't have to worry about carrying C's around. They'll also set H equal to 1, so they don't have to worry about having H around. And then you get another thing, and that is that the wavelength of something is equal to H, let's see, what do you get? You have this thing HC, and this gives you energy is equal to HC over lambda. Okay, so then I can rearrange these things, and I get lambda equals HC over the energy, and that gives me a length. Okay, so this is, HC is, that's Planck's constant, this is the speed of light, and this is the wavelength, the quantum wavelength of some particle, and this is the energy that that thing will have given that wavelength. So if you rearrange this term, you can get a length scale. So when you take the dark energy density, we know what the dark energy density is because we've measured the supernova results and the CMB results and the galaxy clustering results. We know what the energy density of dark energy is. And so you can just put that in here. Okay, this is, you put in a meter, you put in the energy, and you end up getting mass over length cubed. Okay, so this is an energy, right? Energy density. And then you say, oh, look, this is equal to, energy is equal to mass, and this is equal to 1 over energy. And so you put in all the units and you end up with something that is energy to the 4th. This is a 4, by the way. It doesn't look like a 4, but that's a 4. Because you divide by length cubed, and that means you have energy cubed, and then that's in the denominator, and so then it's 1 over that in the denominator, so you invert and multiply, and you get energy to the 4th. And that's where you get this thing from here. That the energy density of the dark energy is 2 milli-eV to the 4th. So milli-eV is an energy, and then you have that to the 4th. And so this is the kind of numerology that physicists will do. They'll say, oh, look, the dark energy scale is 2 milli-eV. And that's why if you wanted to look for dark energy in a laboratory, you would take 2 milli-eV, convert it back into a length, using this relationship, convert it back into a length, and you get millimeter scale. And so you would do torsion pendulum experiments at the millimeter scale in order to look for dark energy. So that's what we talked about, like a week ago, a couple weeks ago. Neutrino masses. The neutrino masses, which is what we talked about last time, is milli-eV scale, again. The weak scale seesaw mechanism, so where would we expect to find stuff? If you take the TeV scale, which is the energy scale of the W and Z particles, like the weak interactions of the nucleus, and then you divide by the Planck mass, you get the milli-eV scale. So all of these things tell physicists, whoa, milli-eV scale, that's going to be interesting. And it turns out that milli-eV scale is shows up. There's a way of arranging or designing experiments so that the EV scale, the milli-eV scale, shows up as optical photons. That you would use optical energy photons to probe the milli-eV scale. And that's if you're doing these oscillation type experiments that I showed when we talked about axions with the light shining through wall experiments. And so that's this experiment for axions. So if anyone's interested in looking at axions, there's I have some VODs where I go into detail about it. But what I was interested in, now that we'd done the axion experiment and we'd excluded that, is to look at dark energy. Okay. Here's a question, is would it be easier to look for dark energy in space? Is there more of it? Yes, the answer is there's more of it in space because there's a larger volume in space, and that's why dark energy was discovered in space with the supernova results and not in a laboratory. And so this experiment that I was on to look for dark energy, turns out did not discover dark energy. If I had discovered dark energy, then I would be famous. More famous than I am now, because I have like dozens. We have 100 people. So that's how famous I am now. If we had even more than that, if I had discovered dark energy in a laboratory, then we'd probably have 200 people. All right, so there is an issue with dark energy. That's the theory, a problem with the theory of dark energy. The vacuum energy should have some ground state to it, right? This was known that the ground state has quantum fluctuations in it. The vacuum has the energy, or the universe has a ground state fluctuation because there's always quantum particles, quantum fields in there. They're always going to be wiggling around. And so that's some energy. And the ground state should be something like this for the smallest box that you can find. The smallest box you can find is the Planck scale. So you put in these numbers and you get 10 to the 124 milli-eV to the fourth. 10 to the 124 is slightly larger than 2, last time I checked. 10 to the $124, which is more dollars than there are atoms in the universe, is bigger than 2. And so this is somewhat of a disagreement between theory and experiment. This will say a small discrepancy of only 124 zeros. Okay, so this is an issue that needs to be resolved. How do you resolve this issue between the fact that when we observe dark energy, it has a very low density, and when we predict dark energy, it has a very high density? Well, this is where the same idea. You have the same idea here for dark energy that what we had with the axion is that you create a new field. You create a new field, and that field is going to cause certain interactions that are going to take place that are going to drive the physics in a particular direction. It's going to drive this basically close to zero, and what we see is the leftover. Okay, and so this is the physicist toolkit. So this is Rocky Cobb. Whoops, I didn't mean to skip ahead. The physicist toolkit, and there are 2 different types of physicists that are out there. There are experimentalists and there are theorists. And the experimentalists have 2 things that they use. If something shouldn't move, or if something should move, but it doesn't, so if you have something that's stuck, you should move it, but it's not moving, then you use WD-40. On the other hand, if you have something that's moving and it's supposed to stick, then you use duct tape. So if something moves but it shouldn't, you use duct tape. The theorists have the same toolkit. They have 2 things in their toolkit. If something is moving but it shouldn't, if something is too floppy and you need to constrain it, then you invoke the anthropic principle. Like, oh, if the universe had too much matter in it, then we wouldn't be here to observe it, so therefore the universe doesn't have very much matter in it. That kind of thing. So this is the anthropic principle. So if you ever predict that some catastrophe should happen, you say, oh, the anthropic principle prevents this from happening because otherwise we wouldn't be around here to observe it. So the theorists have another toolkit for if something is moving, or if something should be moving but it doesn't. The theorists have something to their own tool for that as well, and that is called the scalar field. A scalar field is what you invoke if something should move but it doesn't. If you need to have dark energy, but you don't have any, then you invoke a scalar field. If you need to have an axion, but there isn't one, then you invoke the axion field. So a scalar field is the theorist's equivalent of WD-40. It takes something that is stuck and allows it to move. So it takes a disagreement and allows it to be swallowed up in the physics of that scalar field. Okay, so here is the experimental evidence for scalar fields as of the time that I gave this talk, which was a long time ago. Now we actually do have experimental evidence for scalar fields because the Higgs particle is a scalar field. I gave this talk before the Higgs particle was discovered, although everyone expected it to be discovered basically the year after I gave this talk. So the experimental evidence for scalar fields, this is now out of date. The Higgs field is a scalar field, but it is not the scalar field we are looking for. So we have this problem where the dark energy density is 120 orders of magnitude away from where we expected it to be. And so we need a scalar field to resolve this tension. But there's another problem that you run into, and that is scalar fields are exactly what you would measure if you have one of these torsion pendulum experiments. So torsion pendulum experiments measure scalar fields. That's what they do. And I have discussions about torsion pendulum experiments, and they have found that there are no scalar fields with these couplings. There are no scalar fields that would explain this. And so that's a problem. So given the fact that there's no evidence for scalar fields of this type, so the Higgs notwithstanding, because this is not the Higgs, there's no scalar fields that would produce the dark energy that we expect to find, because it would have shown up in the torsion pendulum experiments. We have to come up with a way to hide those scalar fields. We have to come up with a way to hide the scalar fields. There are three ways to hide the scalar field. And so what you do is you look at the equations that dictate how things operate. This is the Klein-Gordon equation. I stole this from Justin Coury at Penn. So this is a Klein-Gordon equation that basically says, okay, here's a kinetic energy term, here's a mass term, and this gives you a potential, basically is what that says. Here's the density of the particles. So particles can move in space, they have mass, and that gives you the energy density related to the Planck mass. So if you want to hide the scalar field, what you need to do is you need to change its behavior when you get into a detector. So the torsion pendulum experiments, these metal objects, these beryllium copper alloy things, they're made out of stuff. And you want to suppress the coupling of this dark energy when there's this stuff around. When you're in the laboratory, you want to hide it when you're in the laboratory, and you want it to allow it to be free and to interact with things when you're in space. Because we've seen the effects of dark energy out in space. We know that dark energy exists out in space, but it does not exist, at least in a trivial way, in laboratory measurements. So how do you hide something in laboratory measurements and let it be free in space? And the answer to that is, well, you only have three options. You can either mess around with this term, or you can mess around with this term, or you can mess around with this term. Those are your options. This is the equation that you have to worry about, and there are three terms, and so you have to mess around with one of the three. So if you mess around with this term, the kinetic term, it's called the Weinstein effect. I don't really know much about it, so we'll just skip that one and say there's a Weinstein effect that hides scalar fields from laboratory experiments by adjusting this term. You have the symmetron. The symmetron thing is where you mess around with this. That basically says that the coupling, so this G here is the coupling strength. The coupling strength of this scalar field, you just make it so that when there's a lot of density around, so here's the density, when there's a lot of density around, you just change the coupling. So in high dense region, the coupling goes away. Or you can make it smaller, you can make it stronger, but we need it to be smaller. So you can hide the coupling as a function of the density. And then there is the chameleon effect. The chameleon effect is that you basically change the mass, that the mass of the particle changes when the density goes up. So you have an ambient density in your experiment, you have a metal object, and as the dark matter particle gets into that metal object, its mass changes. And when its mass changes, then you have to account for that change in mass, and therefore it actually acts like a reflector. So if you have a dark matter particle coming in, it goes into an area where there's lots of mass, and it just reflects off of it and doesn't actually couple to anything. That's the chameleon effect. So that would allow you to have the following scenario. That would allow you to have a torsion pendulum experiment that we've talked about at some detail. Here's a torsion pendulum experiment. Okay, let me do it like this. Here's a torsion pendulum experiment. And you're looking for a coupling, a dark energy coupling between the torsion pendulum and these source masses, right? Here's the fiber. You have a thing right here. The problem is that the dark energy particle is this chameleon particle. So here's the dark energy particle out here, and it has a strong coupling, strongish coupling. That says coupling, by the way, even though it doesn't look like it. So it has a strongish coupling when it's out here. But then when this chameleon particle comes in and it hits this area here, it says, oh, the ambient density, this is like a solid piece of beryllium copper, and then its mass gets really big. So here's the mass of the chameleon particle. Now the chameleon particle has this huge mass, and it can't penetrate into here. Basically, it comes in, its mass starts to grow, and conservation of momentum says you can't move any further in this direction, and so it reflects off of that surface. So that means that the chameleon particle can't couple to this, which means that it can't couple between these two things either. The chameleon field between these two particles, the coupling is too weak, or its mass is too big, and so it can't exist. Its mass would grow too large, and therefore basically conservation of energy prevents it from existing in that area. So that is the chameleon force, or the chameleon effect. So this is a way to hide a scalar field. So physicists want scalar fields to exist. They want them to be able to explain the presence of dark energy, but there are only 3 ways to do it and still be consistent with the torsion pendulum experiments. And the chameleon effect is one of them. So we designed an experiment that was looking for this. The idea was that you have a laser, you have a vacuum tube right here, vacuum system. It's not a vacuum tube like a television tube. It's a piece of the tevatron, a magnet of the tevatron with mirrors or with windows on both sides, and you send in a laser beam. There's a magnetic field, and this would require a coupling of the chameleons to that magnetic field. You send them in, and then some of these photons will convert into chameleon particles. So now you have this dark energy particle that's trapped inside this container and starts bouncing around. It's trapped in there. It can't escape because every time it tries to escape, its mass grows too big, and that violates conservation of energy, and so it has to reflect off of the walls. So you send in this laser beam into a magnetic field. You produce, with these optical photons, gives you this milli-eV energy when you're doing an oscillation type experiment. Photons come in, they start bouncing around inside, or some small fraction of them convert into dark energy particles. They start bouncing around inside this bottle because they can't escape. And then you turn the laser beam off, and the reverse process, the reverse process is always going on, but you turn the laser beam off, and the reverse process takes place where the chameleon particles that are bouncing around slowly reconvert into photons, escape, and then you detect them in a detector. So it's a particle in a jar type thing. You fill up the jar, and then you stop filling up, and then you let the particles leave the jar, and you measure the rate that the particles leave the jar. And the way that they leave the jar is that the chameleons, they're still in this magnetic field, and so the chameleons convert. So the chameleon is the dark energy particle. They convert back into photons and escape. So turns out that, because unfortunately I need to run, but we did this experiment, and I'll go into detail about this experiment some other time. We did this experiment and we didn't see anything. Well, actually that's not true. We did this experiment and we saw, what did we see? It was a very disappointing few minutes. We saw this. It made me cry. It didn't make me cry, but I cried on the inside when I saw this. So these were our actual data. We're doing this experiment. We're like, okay, let's turn off the laser and see what happens. We turned off the laser and we saw this decaying light in our photomultiplier tube. And this made me very sad. The reason it made me very sad is because I knew that this was wrong because we didn't have the magnets turned on. So the experiment that we ran says that you need to have a magnetic field. Where did I put it? Where's that plot? Here's the plot. The experiment that we ran said you have a magnetic field turned on, and you shine the laser beam in, and the coupling of the laser to the magnetic field is going to produce the chameleon particles, and then the magnetic field is necessary for the chameleon particles to convert back into photons and then escape. We saw the photons escaping this chamber, and the magnetic field was not turned on. These were not the particles we were looking for. This was, anyways, so that took a while to figure out what was going on. So it turns out what was happening, and it took us, we found a way we knew that it was not what we were looking for because the magnetic field was turned off. So we did some calibration stuff. We came up with a method that we would use to analyze the data to remove this effect, and turns out that what ended up happening was this is leftover residual vacuum grease. So some kind of grease that you use in vacuum systems to seal it up tightly. There was some residual vacuum grease. No matter how many times we swabbed out the interior thing here, there was some residual vacuum grease, and that residual vacuum grease was being excited by the photons. The photons were coming in, hitting that vacuum grease, exciting it into some, like glow-in-the-dark state type thing. And then when we turned off the laser, that essentially glow-in-the-dark stuff, the fluorescence, was converting back into photons and sending it back out. And it was coming out the wrong color. So here, notice that it's green light coming in and it's green light going out. And what we saw was it was green light going in, and then it was orange light that was coming out. And so it turned out to be, we called it the orange glow. That's why it was called the orange glow. So here's the orange glow. It had a temperature dependence, which chameleons shouldn't have had. And it turns out that it was due to this residual vacuum grease. So anyways, we didn't discover dark energy. If we had discovered dark energy, you can guarantee that I'd be even more famouser than I am now. All right. So I will go into, at some point in the future, I'll probably go into some of the details, more of the details about this and some of the other experiments that people are doing using the same kind of technology. So here's like the Fermilab holometer, which was to look for the, maybe the holographic universe, to see if the universe was really a hologram. Like what we really did when we did this chameleon experiments and what we're able to constrain from it. But unfortunately, I don't have time to do that right now. So we will come back to this at some point in the future. This isn't like super groundbreaking experimental results because we didn't see anything, but it was fun to do, certainly as a postdoc, to be able to have exclude a large chunk of dark matter possibilities, right? So all of this stuff here is stuff that we excluded. That's like 4 orders of magnitude in this direction and 3 orders of magnitude in this direction. That's a lot to be able to exclude these kinds of physical couplings. But that's for another time when I can go into detail and I have the time to do that.